Welcome to Empowered Learning Videos. This video will be the first video in the series of Laplace Transform videos that I will do. This first video will go over the definition of what the Laplace Transform is, its purpose, and some of its basic properties. I will not go over things like the linearity and translation properties in this particular video. I'm talking about more basic things like what types of functions we could actually take the Laplace transform of and certain things like that. So that's what this particular video will be about. If you are looking for information on how to derive the Laplace transform of a particular function, then this video won't cover that. That will be in my part 2 video. If you're looking specifically for the linearity and translation properties, how that's applied to a function, as well as examples of trying to find the Laplace transform of a general function, you want to check out my part 3 video. Again, this video is strictly for making sure that you have a deeper understanding of what the Laplace transform is and, as I like to put it, its constraints. So we're going to go ahead and get started there. So at this point in this particular course, and I'm talking about a differential equations course, you probably have studied many different types of ordinary differential equation solving techniques. Okay. Now, what the Laplace transform is actually another technique that we're going to use. And essentially what the Laplace transform is, it is an integral transformation. So you're going to take a function, basically throw it into an integral where you're going to multiply that times another select function. And then the result of that is actually going to be area under the curve of some new function. And so it turns out that what the definition ends up being is some improper integral. So you have to make sure that that integral will converge. Okay. And so as long as you have functions that sort of meet the condition of, hey, that improper integral converges, then we know that that particular function that you throw into the whole Laplace transform definition will end up being what we call Laplace transformable. Okay. So that's sort of in a nutshell what it is that we're doing here. Now, from a computational perspective, what it is that we're actually trying to do is we're trying to find a way to solve ordinary differential equations from being so, I'll say, calculus intensive as far as all the techniques that you've probably learned up to this point if you're studying a basic differential equations course. We want to get out of using so much calculus, and we're really trying to turn this thing into a big algebra problem. And so when we do the Laplace transform of a particular function, that's essentially what ends up happening. And so again, we change an ordinary differential equation that we want to solve. We change the techniques of solving it from doing more calculus steps. And of course, there's some algebra in there naturally, but when we do the Laplace transform of a function, what we end up doing is purely solving the problem algebraically at that point. And so it's kind of like algebraic manipulation on overdrive. And that's really what it ends up feeling like. So that's the main idea here. So as I state here, one way we can make this process of solving ordinary differential equations more efficient and less painful is to consider employing techniques called integral transformations. And so the Laplace transform is just one of many integral transformations that we have. We do have other integral transformations that some of you may have heard of, like the Fourier transform integral, Z transform integral, some of the ones that are more popular. But again, the one that we're going to talk about is the Laplace transform, which is probably the easiest to understand out of all the ones that are out there. Now, one thing I did want to illuminate before we kind of move on here is, and I'm going to scroll down in the notes that I have here for just a second. And so you'll see that I have the sentence in here. To be specific, we can transform our equation from looking one way, that is to say, or as example, having terms in the equation that act like functions of time, into another way that might be more useful to us. That, for example, having terms of an equation that acts like functions of frequency. And so I know in engineering, electrical engineering to be specific, we have a lot of situations where we take an ordinary differential equation that is, let's say, modeling a circuit, and we want to study the frequency characteristics of that particular circuit, because that's the thing that's important to us. So when we do a Laplace transform of that ordinary differential equation that's modeling that circuit, what we're actually doing is actually switching from looking at the circuit in the time domain to the frequency domain. And in the frequency domain, we can see things that we could not necessarily see in the time domain, and vice versa. But again, if my circuit has to meet all of these specs, and a lot of them are based upon frequency, then of course I want to look at that particular equation in the Laplace transform equivalent of it, because that's going to communicate all the things that I need to see so I can do whatever analysis I need to do. Of course, there are many other applications of using the Laplace transform. I just know that that's the one that I use it for the most, just off the top of my head. So I wanted to make sure that you had a quick application of why we actually use this stuff before we get deeper into this discussion. So the goal of the videos that I'm going to be doing from part one all the way to whenever I finish, I was going to be able to do several things. Of course, this first video, my main thing that I want to do is concentrate on the Laplace transform definition and communicate its primary purpose. Okay. In my part two video, I'm going to provide examples on how to do Laplace transform of several functions are derived, and illuminate some important properties, mainly the linearity properties and the translation properties. And then, of course, in my part three video, I will do examples of how to actually take the Laplace transform of a general, function. Of course, that'll be along with the linearity properties. So for those of you that are looking for things about the inverse Laplace transform and all that, then of course that'll be later on in a different set of videos. But for right now, I'm just trying to concentrate on the Laplace transform itself. Okay. All right. So I'm going to go ahead and move on here and talk about the actual definition. So the Laplace transform definition, in short, it is an integral transformation. And as you can see, we have what that integral transformation looks like. So notice here again that all it is you're taking some function, select function, and we'll talk more about that later, and we're multiplying it times this decreasing exponential function, and we're going to integrate it from 0 to infinity. Okay, and so because of that, we're doing it from 0 to infinity. We know that this ends up being an improper integral, and in order for this particular Laplace transform of this function to even exist, we know that this integral would have to converge, which means the integral would end up having to equal some real number. Now, if we actually read the definition, we say let f of t be what we call a suitable continuous or piecewise continuous function. And so we're going to talk a lot more about what that actually means, as far as what does it mean to be suitable, as well as we'll cover what it means to be continuous, but more so if we're dealing with a piecewise function, what does it mean to be piecewise continuous? We need to address all those things so that we have a clear understanding of what type of functions f of t we can actually use to perform this Laplace transform. Now, the way that we denote that we've taken the Laplace transform of a particular function, we either do this big F of S, or we note it this way. Okay, so that's the two known ways of denoting Laplace transform. And we'll use that notation interchangeably as it's convenient for us. So at this point, we've seen what the definition of the Laplace transform is, and it's a fairly simple definition, but there's a lot of information packed into that definition. And so when I talked about we want to kind of go over the constraints and the flexibility of this particular transform, we're going to talk about that now. And the bulk of this video is going to be discussing those things as well as summarizing all that we discover towards the end of this video. So the first thing I want to illuminate out of many is that we're changing the form of our function that's in terms of t. So remember, we have a function f of t here. We're changing this function from being in terms of t. And in normal practice, the values of t are assumed to be real. But we do have some cases where we can assume the values of t to be complex as well. But normally speaking, in an application, t is going to represent time. And of course, time is going to be a real valued thing. Okay. So normally speaking, we're taking a function that is defined in terms of some real number t, which we'll assume is time. And we're going to translate it into a function in terms of s. And s could be a real number or a complex number. Okay. And in the example I gave you earlier, we're taking something from the time domain to the frequency domain. And in the frequency domain, most people think of frequency as being real valued, but we do have a complex valued frequency as well. Okay. And so we want to make sure that we have that flexibility to express things in the S domain to be either real values or complex values. Okay. Now, when we talk about what is a suitable function, to put it very simply, what we're saying here is that we want the product of our e raised to the minus st and whatever our function f of t is going to be, the behavior of it as t approaches infinity, it should be going to 0. Okay. So basically what we're saying is that when I combine f of t and e raised to the negative st, is going to end up being a function where the behavior of it is basically approaching the x-axis, or the t-axis in this case, as t goes to infinity. Now, another way to translate that is to say that our f of t will not decrease as fast as our decreasing exponential function e raised to the minus st as t approaches infinity. So that's one way to say it. A more general way to say it, and I'll switch here, is we could say the following. So if we have the limit as t approaches infinity of e to the minus st f of t, we know that we could rewrite this limit this way. Or basically you just put e to the positive st in the denominator. And so here what we're really comparing is how fast does f of t grow compared to how fast does e to the st grow. Okay. And what we're saying here is that if we want our function f of t to be Laplace transformable, f of t cannot grow faster than e raised to the st. So if I was to plug in, infinity for t in this case, we know that the denominator would always grow faster than the numerator. So no matter what f of t is, the denominator here, this would be some constant, this would be infinity, and constant divided by infinity always approaches 0. So that is another way of saying it. Now, I know some textbooks, they get kind of fancy and say that f of t has to be of exponential order, and then they'll name it some value here, and I'll call it just s of 0, which is translating to whatever f of t is, the magnitude of it, or if I looked at the graph of this particular function and I took the absolute value of it, it cannot be a function that lies above this particular exponential function here, okay? And so they go through all that, but basically all it's saying is, hey, if f of t grows or increases or decreases slower than the e raised to the st function, then it means that the f of t function will act at most like this one as far as its increasing or decreasing properties. And because of that, we'll always have this situation here where the product of these two functions will go to 0 as t goes to infinity, okay? So, and that's really the basic idea that you need to get there. So the next thing that we want to illuminate is that for functions that meet the condition that we just talked about, of course, that function times e raised to the negative st is going to be 0. They are what we considered well-behaved functions, okay? And well-behaved is just a nice way of saying that the function will not grow out of control, and thus that improper integral that we have to evaluate, it's actually going to converge. If we picked some function f of t to where the product of f of t and e raised to the minus st would not be well behaved, then it would grow out of control and our improper integral would diverge in that case, okay? And of course, we don't want to deal with functions that make that happen. So the next thing that we want to talk about is how is this function going to be Laplace transformable in terms of the types of equations that it deals with. And I'm talking about differential equations here. So in short, what I'm trying to say is that the functions that f of t that are good candidates of being Laplace transformable are going to be those same functions that we would use, let's say, for ordinary differential equations, non-homogeneous type, where we use method of undetermined coefficients. So those types of equations that we would say, well, yeah, I could solve that ordinary differential equation that's non-homogeneous by using methods of undetermined coefficients. If I could apply that method to the differential equation to solve for its general solution, or a particular solution to be specific, then those are the same types of functions that are Laplace transformable, okay? So that consists of your constant functions, your exponential functions, your polynomials, and sine and cosine, okay? So in terms of continuous functions, these will be those types of functions. Now, of course, on the piecewise function side, we could have a combination of any or all of these, but it really just depends upon if that particular function is going to be what we call piecewise continuous, okay? And we're going to get more into that, but just from a simple general standpoint, if you have a constant function, an exponential function, and of course with the exponential function, if we're looking at e raised to the minus st versus this thing that I came up with earlier when I was talking about exponential order, we know that whatever the value of s is, it's going to have to be higher than the value of this s sub 0, okay? So when we talk about exponential functions, got to meet that condition. Any polynomial, any cosine or sine function, okay? So I'm going to erase this, and now that we kind of know what functions, we have a good idea of what type of functions are Laplace transformable, I'm going to go and talk about this phrase here. Finite number of functions that can be used to express a derivative of that function. So what that basically means is that all the functions that I've listed here, constant function, exponential function, polynomial function, sine or cosine, we can either, if we wanted to find the nth derivative of any of these functions, the nth derivative of it would either be 0 or it would be some variation of these functions here. So to kind of make my point, I'll make some more room here. So let's say if I took the derivative of x squared, of course that would be 2x, and I took the derivative of 2x, that'll just be 2, and I take the derivative of 2, that's going to be 0, okay? So we know that for x squared, the third derivative would end up being 0. If I want to take the derivative of sine, of course, the derivative of that is cosine. If I want to take the derivative of cosine, we know that that's going to be minus sine. And of course, derivative of minus sine is going to be minus cosine. And derivative of minus cosine is going to be sine again. Okay? And so my point here is that if I kept on taking derivatives of sine, I would keep on going through this cycle of cosine, minus cosine, sine again, all over again, okay? And so what this is telling us is that we have a finite number of functions that we could use to be able to express the derivative of x squared to any nth order, as well as with sine, okay? So with sine, the two functions that could be used to express any order derivative would be sine or cosine. With x squared, we would have, of course, 2x, 2, and 0, okay? So finite numbers. So that's what we mean by that. Functions that have one of these two properties here, we know are candidates for being Laplace transformable. That's the point that I'm trying to make. All right, another thing that we want to take into consideration whenever we are doing the Laplace transformable function is that for values that are negative, they're irrelevant in the Laplace transform, okay? Now, part of that is because of the fact that the way that we defined it, if you remember, is from 0 to infinity of e raised to the minus st times f of t dt. So we're not considering these values in the first place, okay? So part of the reason for that is in one of the major applications of a Laplace transform is using it in what we call linear time invariant systems. And that just basically means that the time in which we have something happen to that particular system doesn't have any bearing on what that output's going to look like, okay? So let's say if 3 seconds from now, I was to apply some kind of, impulse to an electrical system. It doesn't matter if I did it 3 seconds later or if I did it 10 seconds later. It's pretty much going to act the same way if I'm doing the same action. And so because of that, it just doesn't make sense for us to evaluate what's going on at times t being negative, okay? Now, from a math standpoint, if I allowed t to be negative, then that means that e raised to the minus st at this point is going to be an exponentially increasing function. And I know if e raised to the negative st is exponentially increasing, then if I was to multiply this exponentially increasing function times whatever function this is, it's just going to grow out of control. And so I don't want that because that's not going to help me have a convergent improper integral for my Laplace transform. So that is another reason from a math standpoint or a computational standpoint, we don't want to worry about values of t being negative. And so here, this is just me stating that in the notes here. Mathematically speaking, if we consider times to be negative, then of course, we're looking at this situation here. The limit of the product of these two functions here would just basically grow to infinity. And of course, we don't want that, okay? Now, I make this statement here because even though we're doing the Laplace transform, I want you to have a general understanding of what integral transforms are, okay? So whenever we do a basic integral transform, most of them are going to look like this. The limits of integration here may change, but basically what it is we're taking some function and we're going to multiply it times another, and then we're studying the area under the curve of that function, okay? Now, depending upon what this function k of st, so this is a function of two variables, we're going to say, depending upon what this is, depends upon what is suitable to be able to perform this transform here, okay? Since we are choosing in this case to have exponentially decreasing functions being multiplied by our f of t, then what is suitable to put into this integral here and evaluate it and expect to get a convergent result is that whatever function that we put in there has to grow slower than, or at the very least, grow at the same rate as e raised to the negative st, okay? And when I say grow, I mean increase or decrease. So if you want to look at it this way and have it over 1, then of course, if you just look at the denominator, I'm talking about how fast it grows, okay? If you're looking at it as e raised to the minus st, we know that's an exponentially decreasing function, so we want to know how much it decreases, how fast it decreases, okay? All right, so now what we're going to do is talk about the role of continuity in selecting suitable values of f of t, okay? Now, whenever we talked about suitable values of f of t, we gave the list of constant functions, exponential functions, polynomials, sine and cosine. So we gave those examples there. All of these functions here meet the condition of they will be what we call continuous on an interval from 0 to infinity. And we're actually including 0. And so from first year calculus, we know that what this means is that the limit of our function f as t approaches some value t sub 0 here is going to equal to the same y value for our function if we were to allow if we allowed t to be t sub 0, the corresponding y value would be the same as what this limit would come out to be, okay? And that happens for each and every value of t sub 0 on this particular interval. So we know by definition that means that our function's continuous, okay? Now, if we're looking at situations where our function is not defined at t equals 0 for some reason, we still know that the behavior of our function as t approaches 0 from the right of it is still going to be f of 0, okay? So we're just stating that to say that whatever function of f of t that we have, which is normally going to be these types of functions here, if they are just straight up continuous, they're going to satisfy these two properties here, okay? Now for piecewise continuous functions, it's going to be a little different, okay? The main things that we need to know about a piecewise function to make sure that it is piecewise continuous is that, number one, it has a finite number of jump discontinuities. So to show you an example of what that looks like, let's consider this function here, y of t. If you notice here, y of t has 2 jump discontinuities here. And notice that for each place or location where we have a jump discontinuity, if I took the limit of this function as t approaches, let's say 2 from the left, and t approaches the limit of y of t as t approaches 2 from the right, you'll notice that the limit of the function coming from the left and from the right both equal a real number. In this case, limit coming from the left of t equals 2 equals a value of 4. Limit of function as t approaches 2 from the right ends up being 2. Okay. Also at 4, we see that limit of the particular function as t approaches 4 from the left is going to be 3. T approaches 4 from the right, limit's going to be 4. Okay. And so all we're saying is that for our function to be considered to be piecewise continuous, we are saying that we have to have a finite number of these jump discontinuities, meaning that we can actually count them. Okay. So that's one thing that we have to meet there. The other thing, of course, is that we have to have the case where at these jump discontinuities, the limit from both the left and the right of that function are going to have to both exist at each location. Okay. Now, what I can't have is something like this, and I'll just sketch something really quick so that you can kind of see the difference here. So let's say I started off and I had a function that was like this, and then let's say I came here, and let's say my function did something like this. So I had a vertical asymptote here. And then, of course, let's say at 2 again, this function now comes down like that. So on this side of the vertical asymptote, it's defined, but on this side, it isn't. And of course, the limit here, as t approaches 4 from the left of, let's say, this function g of t, that's going to go up to infinity. And so if I have a situation where I have jump discontinuities that look like this, this is not what I consider to be piecewise continuous. Okay, it is not that, because every jump discontinuity has to have a situation where the limit on the left and the limit on the right of that particular number where the jump continuity is, the limit has to exist on both sides. Okay. And so as long as we're dealing with functions like that, we are able to take the Laplace transform of it. Okay? If we're dealing with functions like this one, then we can't take the Laplace transform of it. So we see here that for our function f of t to be Laplace transformable, one of the properties, not the only property, but one of them, is that either the function is just going to be continuous straight up for all values of t, from 0 on to infinity, or it may be some subset of that, because let's say, for instance, we have a function to where it starts at t equals 3. Then, of course, we can't go from 0 to infinity in that case. We'll just have to go from 3 to infinity. So we'll have some case where it's straight up continuous, or it is going to be piecewise continuous. And, of course, I just described that. Now, if a function is going to be considered to be Laplace transformable, it will be that if and only if. So now I'm kind of drilling down and telling you what has to be true. Okay. And when I make that statement of if and only if, of course, that means that if a function meets all 3 of these conditions I'm going to state, then that means it's Laplace transformable. And if the function is Laplace transformable, then it means that it meets all 3 of those conditions. So in other words, it's inextricable. Those things go together. One can't happen without the other. Okay. I know some math people like to say it's necessary and sufficient. Okay. So the first thing is that the function either has to be continuous or piecewise continuous. That's one thing. Second thing is this limit here has to equal 0. And to put this conceptually, the function f of t cannot grow faster than the function e raised to the st, Or if we look at it in this case, the function f of t cannot decrease faster than e raised to the minus st, okay? And if that happens, then of course the limit of this product of two functions goes to 0. Third thing is that our function must be well defined. And so we usually don't have to worry about this situation here because with the functions that we normally deal with, if we can actually say that the relation that we're looking at is indeed a function, then of course by definition it's going to be well defined. It won't be ambiguous. When we start to deal with more complex functions, and this is mainly for stuff that's not the exponentials, the sine, cosine function, like most of the functions you normally deal with, and it's really for like higher math type stuff where they have some funny defined functions. Or in the case of, let's say, a piecewise function, well, a piecewise relation, if that piecewise relation isn't a function, then that would kind of violate this condition here. But for the most part, you won't, rarely if ever, have to worry about this part. All right, so one of the last things I want to talk about is the uniqueness of the Laplace transform as it relates to a function f of t that we're trying to transform that function from f of t into the Laplace transform. And so the main thing to know is that the Laplace transform is not unique, okay? Now, the simplest way that I could put this is that remember that the Laplace transform in and of itself is an integral, which means that if we're looking at this in a two-dimensional sense, we are trying to study the area under the curve of some function as t goes on to infinity, okay? Since we're looking at it as area under the curve of a function, notice that these two functions here, a of t and b of t, which are both piecewise continuous functions, notice that they both have the same area under the curve. If you're assuming that both of these functions here are equal to one another, okay? I tried to draw them to make sure that they were equal. Just assume that this one and this one look the same. The only thing that's different here is that my a of t function is defined at t sub k, whereas my b of t function is not. But we know that our jump discontinuities do not contribute to area under the curve of this function, so therefore they're not going to contribute to what the Laplace transform of a function, a of t or b of t would be in this case, okay? So because of that, we know that the Laplace transform of a of t and the Laplace transform of b of t would end up being the same Laplace transform because the area under the curve of these two functions would indeed be the same. Now, if we wanted to look at this from a computational standpoint, we would see here that if I was to evaluate the integral of e raised to the minus st times f of t dt from 0 to infinity here, we could break this up into three separate integrals, where we know that this integral here, because of the zero width property for integration, we know that for both functions, it would end up being 0 because, again, if we evaluate any function at any value with the definite integral, going from one value to that same value, of course, that result is always 0. And of course, we see that in this case, that this improper integral here is just basically the sum of these two integrals here, which is the same as the a1 and a2 that we saw up here, okay? So saying that because sometimes we're going to deal with some functions that can be defined several ways, or we're going to deal with functions to where even though they look different, we may end up having the same Laplace transform of them, depending upon what it is, kind of like this situation here. And we don't want you to be surprised by that. All right, so we've kind of done a deep dive into what the Laplace transform is all about as far as what is its definition and the type of functions I can consider. I just want to do a quick summary just to make sure that we all got it before we move on to the part 2 video and talk about deriving some basic Laplace transforms of basic functions that we use. So the first thing is that we know that this is the definition. It is an integral transform, and we're basically taking our function, multiplying it by a decreasing exponential function, and we're doing an improper integral from 0 to infinity. And we know that this integral must converge. Okay. The next thing that we know here is that if we're doing a Laplace transform of f of t into big F of s, then we know that it is possible for the values of t to be real numbers and the values of s to be complex numbers. So we will translate from real numbers to complex numbers. It's also possible for us to translate from complex numbers to complex numbers. So it is possible for t to be a complex number. Kind of rare, but it is possible. And we also have the situation where we can have t being a complex number, and in the Laplace transform, or in the S domain as we'll call it, we'll actually end up having real numbered value functions there. Okay, so that is possible. So we also know that for our function f of t to be considered to be Laplace transformable, another way of saying that is it's a suitable function. We know we have the 3 conditions. The first is that our function either has to be continuous or piecewise continuous. And remember, piecewise continuous just means that the limit of our function at each of the jump discontinuities that we have from both the left and the right have to exist. And on top of that, we know that there is a finite number of jump discontinuities in our function to begin with, meaning that we can actually count the number of jump discontinuities is going to be. So that's our first condition. Our second condition is, of course, that the behavior of e to the minus st times f of t approaches 0 as t approaches infinity. So in other words, my function f of t cannot grow faster than e raised to the positive st if I want to think about it in terms of increasing terms, or if I think about it as e raised to the minus st, the rate in which this decreases has to be faster than the rate of which f of t either increases or decreases. It really doesn't matter. Okay, and of course the assumption here is that, or another way of putting this rather, is that f of t is of exponential order s sub 0, where s sub 0 is always less than whatever value s is here. Okay, and then of course the third one is that f of t is going to be well defined. So basically it just means that, hey, the function is not defined in a confusing way. So those are the 3 conditions that we have for a function f of t to be what we call suitable. Okay. We know that suitable means, in terms of the growth of the function, that the product here is not going to grow out of control as t approaches infinity, and that's one of the reasons why the behavior of it kind of goes towards the t-axis as t approaches infinity. Okay. So again, if we deal with a piecewise function, it must be classified as a piecewise continuous function. And so an example of what that would not be is we have an infinite number of jump discontinuities in our piecewise function, or we have a situation where at one of our locations, or at least one of our locations where we have a jump discontinuity, we know that the limit as t approaches that particular location, either from the left or from the right, approaches infinity or negative infinity. Okay. We know that our values of t that are negative are irrelevant in our Laplace transform. We don't care about that at all. Doesn't make any practical sense to us, and we know mathematically the integral would diverge in that case anyway, okay? We also know that if we're talking about piecewise functions, the jump discontinuities will not contribute to what the Laplace transform of a particular function f of t would be. So we do not worry about trying to figure out what's going to be the Laplace transform at a jump discontinuity, okay? So now that we've illuminated all these things, the next thing that we're going to do in the next video I'm going to make will be taking functions that we know of, basically those exponential functions, the sine functions, cosine functions, constant functions, quadratic functions, your polynomials in general. We're going to take functions like that and actually perform the Laplace transform of them. The goal of the next video will be to sort of get a collection of functions and their corresponding Laplace transforms so that we can come up with a table. And so in practice, what we would do is get the table, look at the table, and then from that say, hey, I need to take this function, translate it into a Laplace transform. So we would just look at the table and make whatever adjustments that we need to be able to make that happen. And so we're going to talk about more about those things in the next two videos.